You ever just look up at the night sky and wonder, how on earth do we know how far away any of that stuff is?
Oh, absolutely.
Not just the moon or Mars, but, stars, other galaxies. It feels, well, impossible sometimes.
It really does, because you can't exactly stretch a cosmic tape measure out there, can you?
Huh, no.
Figuring out those vast distances, it's been one of astronomy's most persistent and fundamental challenges for centuries.
Right.
Because knowing the distance, that's what lets us turn how bright something looks into how bright it really is. It's true luminosity.
And that tells us about the scale, the age,
Exactly.
the expansion of the whole universe.
Exactly. It's foundational.
And that's exactly what we're diving into today. The cosmic distance scale, this incredible system of methods and tools we've built sort of piece by piece to map the universe in 3D.
Yeah, this ladder we've constructed.
And we've got a great stack of sources here, really digging into this and highlighting the pivotal role that space missions have played. First Hipparcos and now Gaia.
Right, those astrometry missions have been game changers. So our goal in this deep dive is to pull out the key insights from these papers and notes. We'll look at the historical hurdles, explore the current big debate, that really fascinating Hubble constant tension, and see how all this new data, especially from Gaia, is being used right now to try and resolve it.
And it's worth remembering just how tricky even, quote, nearby was. Hysterically, isn't it? Our sources really hammer this home.
They really do. I mean, it wasn't that long ago, relatively speaking, that even the distance to the Hyades cluster...
Which is pretty close, galactically speaking.
Oh, yeah, it's practically in our backyard, maybe 46 or 47 parsecs away. But even its distance wasn't considered fully secure.
Wow.
And we're talking just maybe 25 years or so before Hipparcos delivered its main results back in 1997.
So just nailing down those first few rungs of the ladder was a huge deal.
Absolutely. It tells you how fundamental, how close the distances were that we were still wrestling with.
So if Hyades was uncertain, anything further must have been, well, relying on shakier ground.
It wasn't pure guesswork, but yeah, the methods definitely had much larger uncertainties built in, and that's really why Hipparcos was such a revolution.
Okay, talk about Hipparcos then. What did it do?
So Hipparcos measured parallax. That's the tiny apparent shift in a star's position as the Earth orbits the sun.
Like holding your finger out and closing one eye than the other?
Exactly, that principle, yeah. But for stars, the shift is minuscule. Hipparcos measured it with unprecedented precision for thousands of stars.
And that gives you a direct geometric distance, right? No assumptions needed, just geometry.
Precisely. It provided the first really solid geometric distances for a whole bunch of nearby stars, a fundamental calibration.
Okay, so Hipparcos nailed the distances for closer stars using geometry. How did that help us figure out distances to things way, way further out, like, say, other galaxies?
Yeah, good question. This is where the idea of standard candles comes in. It's absolutely crucial.
Standard candles, like objects with a known brightness.
Exactly. They're classes of objects whose true intrinsic brightness or luminosity we think we understand pretty well.
Okay.
So if you know how bright something really is, and you measure how bright it looks from Earth, the difference tells you how far away it must be.
Right, like knowing a lighthouse always uses a 100-watt bulb. The dimmer it appears.
The further away it is. Perfect analogy.
Got it. And Hipparcos helped us figure out the true wattage of those cosmic light bulbs.
That's the key. By providing precise parallaxes for examples of these standard candles that were close enough for Hipparcos to measure directly. Things like certain types of pulsating variable stars called Cepheids and RR Lyrae stars, or certain types of red giant stars known as red clump giants.
Right.
Hipparcos gave us their geometric distances, and by combining that with how bright they looked, we could calculate their true brightness much more accurately than ever before.
Ah, okay. So once you know the true brightness of the local ones,
you can then spot similar objects, Cepheids, RR Lyrae, red clump giants in more distant galaxies, measure how bright they look, and use that calibrated true brightness to calculate their distance. They become cosmic mile markers.
So Hipparcos didn't directly measure the distance to, say, the Large Magellanic Cloud?
No, too far for direct parallax measurement back then.
But it massively improved the calibration of the tools, the standard candles that we then use to measure the LMC and other distant objects much more reliably.
Precisely. The focus after Hipparcos really shifted. With the local calibration so much better, astronomers could then try to nail down the distances to these key stepping stones, like the LMC, using these refined standard candles.
Makes sense.
And the sources, yeah, they list a whole bunch of standard candles used around that time, both younger ones, population I objects like Cepheids, and older population 2 objects like RR Lyrae stars found in globular clusters.
And Hipparcos data fed into improving most of those methods.
Most, but not all. Things based on, say, eclipsing binaries or that famous supernova in 1987, SN 1987A, those were kind of independent. But for Cepheids, RR Lyrae, red clump giants, and also using subdwarf stars to estimate globular cluster distances and ages, Hipparcos was huge.
So it really firmed up the foundations.
Definitely. Although the sources also note it can get a bit confusing reading the literature from that time because people use different paths or chains of calibration to get to a distance.
Right, like using one method to calibrate another, which then calibrates a third.
Exactly. Like using globular cluster distances derived one way to get the brightness of RR Lyrae stars, and then using that to get the LMC distance. Or using a different method entirely for the RR Lyrae brightness. Lots of cross-checks and sometimes slightly different results depending on the path taken.
Okay, so Hipparcos gave us a much more solid footing for the bottom rungs of this cosmic distance ladder. Where has that journey led us today? What's the big focus now?
Well, fast forward to the present, and the major focus, as these sources really dive into, is this fascinating discrepancy. It's often called the Hubble constant tension.
Ah, yes, H naught, the expansion rate of the universe.
That's the one, H0. It tells us how fast the universe is expanding, and the tension comes because we currently have two main ways of measuring it, and, well, they don't agree.
The early universe versus the late universe methods, right? I've heard about this.
That's it. The early universe method is based on studying the cosmic microwave background, the CMB.
The leftover heat from the Big Bang.
Exactly, the echo of creation. Missions like WMAP and especially ESA's Planck satellite have mapped this ancient light with incredible precision.
And the patterns in that light tell us about the early universe.
They do. The tiny temperature fluctuations contain information about the universe's fundamental ingredients, its geometry, and its expansion rate way back then, just a few 100,000 years after the Big Bang.
Okay, and what value for H0 does Planck give us?
The value derived from Planck's incredibly detailed CMB map is around 67.7 kilometers per second per megaparsec, plus or minus about 0.4.
Okay, 67.7. And the late universe methods, how do they work?
Those are essentially extensions of the distance ladder techniques we've been talking about, pushed out to much larger scales, looking at the universe now or relatively recently.
Using those standard candles again.
Yep. You measure how fast distant galaxies are moving away from us. That's their redshift, which is relatively easy to measure accurately. Then, the hard part, you use standard candles like Cepheids and especially type Ia supernovae, which are incredibly bright, exploding stars, to figure out their distances independently.
And what H0 value do those measurements give?
That's the crux. The H0 values derived from these late universe measurements, looking at things relatively nearby in cosmic terms, consistently come out higher, usually around 73 or 74 kilometer SMPC.
73 versus 67.7. That doesn't sound like a huge difference to a layperson, maybe.
But the key thing is the precision. Both sets of measurements now claim very small error bars. Small enough that these two values, 67.7 and 73, are statistically inconsistent. Their uncertainty ranges don't overlap.
Okay, so it's a real disagreement, statistically speaking.
Absolutely. It's about a 4 to 5 sigma tension, which in physics means is highly unlikely to be just a random fluctuation.
Wow. And that tension is a huge puzzle in cosmology right now.
It really is, because it suggests one of two things, basically. Either there's some hidden systematic error, some mistake we haven't found yet in one or perhaps both sets of measurements,
Right.
or, and this is the really exciting possibility, our standard model of cosmology. The framework we use to understand the universe's evolution might be incomplete.
You mean there might be new physics involved?
Potentially, yes.
Yeah.
Something that affects how the universe expanded differently in the early times, which the CMB reflects, compared to how it's expanding now, which the distance ladder measures.
And this is where Gaia comes back into the picture, right? To try and help resolve this tension.
That's the big hope, yes, and why Gaia is so incredibly crucial right now. As the sources highlight, while the CMB measurements from Planck are astonishingly precise.
Yeah, that 67.7 number seems pretty tight.
It is. The late universe distance ladder measurements, historically at least, have larger uncertainties, especially systematic ones. So the consensus, as laid out in some of these review papers, is that the main onus for improvement, for potentially resolving the tension, currently falls on the late universe side.
We need to make those measurements as precise as the CMB ones.
Essentially, yes. Or at least understand their uncertainties much, much better.
And Gaia is doing for today's distance ladder what Hipparcos did before, but on a grander scale.
In a way, yes, but it's like Hipparcos on steroids. Gaia is measuring the positions, motions, and parallaxes of an unprecedented number of stars over 1 billion stars.
1 billion.
With astonishing precision. This is providing a new, incredibly accurate, geometric, direct calibration for many standard candles. Not just Cepheids and RR Lyrae stars, though it's doing that for many more of them and much further away than Hipparcos could.
Okay.
But it's also proving crucial for other important distance indicators, like something called the tip of the red giant branch, or TRGB.
TRGB. What's special about that one?
Okay, so the tip of the red giant branch is basically the point where a red giant star, one that's finished burning hydrogen in its core and is now burning it in a shell, reaches a specific peak brightness. This happens just before helium fusion ignites in its core the helium flash.
And that peak brightness is consistent.
It turns out, yes, for stars in older metal-poor populations, this peak brightness in certain colors of light is remarkably consistent, almost like a standard bulb switching on briefly.
Another standard candle then.
A very useful one, yeah. Especially for measuring distances to galaxies or parts of galaxies dominated by older stars, like their halos. And Gaia's precise parallaxes for lots of nearby red giants are helping to confirm and calibrate this consistent peak brightness extremely accurately.
So Gaia isn't just relying on one type of standard candle, it's helping calibrate multiple types, Cepheids, RR Lyrae, TRGB.
Exactly. It's firming up the calibrations for several key anchors and rungs of the distance ladder simultaneously. It's really tightening up the measurements at the base and the first few steps.
And what are the specific steps being taken using Gaia data, according to the sources?
Well, the sources detail a whole program of work, really.
Yeah.
First, there's a huge effort just investigating Gaia's own data for any tiny systematic errors or zero-point offsets, making sure the parallaxes themselves are as accurate as possible.
Right, calibrating the calibrator.
Precisely. Then using these refined Gaia parallaxes, especially combined with infrared measurements, which are less affected by dust, to really nail down the absolute brightness, the 0 point of pulsating stars like Cepheids and RR Lyrae.
Okay.
Yeah.
Also, improving the theoretical models of how these stars actually pulsate. Developing really sophisticated computer simulations of their interiors.
That helps interpret the observations better.
Definitely. And then, a big one. Using Gaia's local calibrations to better understand how things like the star's chemical composition, its metallicity or its age, might slightly affect the brightness of these standard candles. These are called population effects.
So a Cepheid in one environment might be slightly different from one in another.
Potentially, yes, or its period luminosity relation might shift slightly. Gaia allows us to calibrate these effects using stars in our own galaxy and then apply those corrections when we look at stars in other galaxies like the Large Magellanic Cloud.
Makes sense. Ensuring consistency.
Exactly. Verifying that the distance scales derived from the younger population I candles, like Cepheids, match up with those from the older population II candles, like RR Lyrae and the TRGB within nearby systems.
Are they checking this in just the LMC? The LMC is a key anchor, but the sources also mention looking at other nearby galaxies, like Andromeda M31, as alternative anchors for the distance scale, spreading the risk, so to speak.
So the overall goal is to use Gaia to shrink those error bars on the late universe H0 measurement down significantly.
That's the plan. The aim mentioned is to eventually get the late universe H0 measurement down to maybe 1% accuracy.
Wow, that would be incredible.
It would, and at that point, we should hopefully be able to see clearly whether the tension with the CMB value persists or if it dissolves away because we found some subtle systematic error in the ladder.
Is it possible the problem isn't with the standard candles Gaia is calibrating, like Cepheids or TRGB, but maybe higher up the ladder, like with the Type Ia supernovae?
That's definitely part of the ongoing investigation. Interestingly, one of the sources mentions recent work using a different type of supernova, Type II supernovae, which come from the collapse of massive stars, not exploding white dwarfs like Type Ia. And the results from those Type II supernovae, while maybe not yet as precise, seem to yield H0 values consistent with the higher late universe numbers derived from Cepheids and Type Ia supernovae.
So that suggests the Type Ia supernovae themselves might not be the sole source of the discrepancy.
It perhaps points away from type I supernovae or maybe even Cepheids being the only problem. It adds weight to the idea that the tension might be real or that any systematic error is perhaps lower down the ladder in the fundamental calibrations that Gaia is working on.
Very interesting. So the plot thickens. Are there any other potential standard candles being explored?
Yeah, the field is always looking for new tools. The sources mention a couple of other possibilities getting attention with Gaia data. One is a type of eclipsing binary system called W Ursae Majoris, or W Umae stars.
Barnett binaries, right?
Yeah,
Where the stars are basically touching.
that's them. Studies using Gaia data found a surprisingly tight relationship between their orbital period and their luminosity for nearby systems. There are apparently tens of thousands of these, identified by Gaia, that could potentially provide distances within a few thousand parsecs.
Another potential rung for the ladder?
Possibly, yeah. And another one mentioned is using the central stars of planetary nebulae, the hot cores left behind by sun-like stars at the end of their lives. There's work investigating if they can be used as standard candles, again using Gaia parallaxes for calibration.
So lots of avenues being explored. It really highlights how dynamic this field is.
Absolutely. It's a very active area, using this flood of Gaia data to refine old methods and explore new ones. There's also a nice readable account mentioned in the sources, kind of summarizing the history and the role of space missions if you want a broader overview.
Good to know. So let's just step back for a second. Why does all this intricate work from, astronomers centuries ago struggling with the distance to the Hyades cluster to today's researchers meticulously calibrating Cepheids and TRGB using Gaia, why does this actually matter to you listening right now?
That's the crucial question, isn't it? It matters because the cosmic distance scale is absolutely foundational. It underpins almost everything we know about the universe beyond our solar system.
How so?
Well, every time you see a stunning image from Hubble or Webb of a distant galaxy and you hear scientists talk about its size or how old it is or how much energy it's putting out, all those figures ultimately rely on knowing how far away it is.
Without the distance, you can't convert apparent properties into real ones.
Exactly. And resolving this Hubble constant tension. It isn't just astronomers arguing over the third decimal place of some obscure number. It's a potential crisis point for our standard model of cosmology, the lambda CDM model.
The model that describes the universe's composition and evolution.
Right. Getting 8-0 right is fundamental to calculating the age of the universe, understanding dark energy, testing general relativity on cosmic scales. If the tension is real and points to new physics, it could fundamentally change our understanding of the cosmos.
It's almost like the universe is presenting us with this puzzle, this discrepancy, and solving it could potentially rewrite the textbooks.
That's a great way to put it. It's a really exciting time in cosmology because of this.
Okay, so as we wrap up this deep dive, here's something to maybe chew on, building directly on that Hubble tension we've discussed.
Go for it.
If, in the end, these incredibly precise measurements from Gaia and other late universe techniques force us to revise our distance scale downwards, making the local universe expand slower, matching that early universe value derived from the CMB, what might that imply? Does it mean our understanding of those standard candles was slightly off? Or could it hint at something unexpected about the physics governing the very early universe imprinted on that CMB echo?
That's one possibility. A subtle error in the latter.
Or, flip it around. What if the late universe measurements hold firm at that higher value, around 73? Could that possibly point towards some subtle, previously unrecognized systematic effect in how we analyze the CMB data itself? Or, more profoundly, does it confirm that the expansion rate has changed in a way our standard model doesn't account for, requiring new physics, maybe related to dark energy or dark matter?
It forces us to question our fundamental assumptions, either about our measurements or about the universe itself.
Exactly. This tension isn't just about getting a number right. It's a potential signpost, pointing towards either hidden flaws in our methods or, maybe, a missing piece in our grand cosmic puzzle, something new about the universe waiting to be discovered.